So last time we talked about how to two-variable function. So today I'm going to do a little bit similar, different, which is I want to explain how what we have done last time is a kind of imperfect. So let me show you what's going on when I put a random function in our code. So last time, this is our code. So we had two types of function, which is x squared plus y squared, or 2y squared equals to z. And another one is the one independent variable and three dependent variable. And we see that this is a spiral trajectory in three-dimensional space. And of course, we have to run one of them. So there's nothing wrong here if you just graph this. Let's see, save, and go run, go. Then, so it says I imported math and not used it. So let's rerun it. So this is our graph of z equals x squared plus 2y squared. But let's think about the weird function, weird two-variable function. This is a very nice function. I'm going to give a very weird function. So for example, so you have to switch the screen. So let's say we have x plus y divided by x squared plus, or y squared here. And let's say this function is defined as long as this denominator is not 0. So denominator 0 whenever, only when x and y are both 0. So this function is defined in entire plane except for the origin. So let's say my domain is entire two-dimensional plane except 0, 0. So I just omitted one point from the domain. So I can draw the value of function, or I can calculate my value of function except for the origin. So I can draw the graph for the almost entire plane. So what's going to be the graph of this kind of function? Let's find out by plugging into the formula here. So instead of nice function like this, I will take that expression divided. So I take square root of x squared plus y squared, and that is my value. I forgot the parenthesis here. Okay. All right. Oh, this is x. Okay. I have to import math because I used here. Okay, so no error. So let's run it. Go run main.go. So you see there are error message. Test PNG is not changed because the program was aborted before I saved the file. So when does it aborted? So you can follow the error message, and it says panic, runtime error, invalid memory address, or nil point difference. So it happens when you have you're accessing a array element which is not defined, or nil value. it's hard to find out the actual place where error happened, but you can guess by looking at your code where this error happened. So let's look at mbf.go. So only places that we are having trouble, possible trouble, is when we are evaluating the function. So evaluating the function at the point where we take the grid point of our domain. So in the main function, we had -2 to 2, -2 to 2 is our domain where we draw the function. Although the entire function domain for the entire domain is the entire plane, we cannot draw the entire plane, of course, in a finite canvas. So when we draw -2 to 2, -2 to 2, we had n number of grid point from -2 to 2 for x and y. So here's our box from -2 to -2. And how many subdivisions did we had? So we have to actually went through. Okay, so we had n subdivisions. For example, how many n subdivisions did we have? So let's go to our code. N was the number of subdivisions. We had 20. So for example, I cannot draw 20 lines here. So let's say make it 10. I will make it 4. So if you make 4 subdivisions, this is our grid line, right? So we are taking a function value at every grid point at these points. So where do you guess the problem was arise? At the origin, right? So we are taking value 0, 0 as one of the grid point and plug into the function, and we have no value here. So maybe the problem will solve if we change the number of subdivision as an odd number, right? Then we can skip the origin, right? So let's see what happens when I change n to 21. Okay, so no error. Let's see the figure. So figure looks like a weird thing going on. So it seems like at the origin, the function value is getting increasing, right? But we don't know whether it goes infinity or it's smooth or anything. So what we have to do is try to find out more what's going on in or about the origin. And also, it would be better if we can rotate this figure. So when we made this code, we didn't have any functionality of rotating this graph. So what we are going to do today is to make our graph function to be able to rotate the graph. But for now, why we are trying to do this? Because we want to see the limit of this point at the origin. So let's think about the concepts first. In the single variable function, the limit of a function when x goes to a is, how do you define it? How did you learn the definition of limit? Right, but so the answer was if f is continuous, then the limit is f of a. But that's uh, that's a spiral argument because we need to define limit in order to define continuity, and once you have continuity, you cannot define the limit the other way. So limit is the prior concept than the continuity. But it's a nice try because if you know the graph of function, which is continuous function, then how do you compute the limit? Suppose that your graph is continuously connected. Then if you want to find out your limit when x goes to a, then what do you do? Right. That's a good try. So actually, x doesn't have to go from the left. It can go from the right. So you check the value of function by changing your x from left of the a and right from right of a, and then see where the value of function approaches. And if it approaches to the same value, say here, then we're saying that the limit is this value. So if it happens to be the same value of the function at a, then we say it's continuous. So it's an intuitive way to define it, but in mathematics there is a formal definition of limit using epsilon delta. Usually the epsilon delta method of definition is the gateway to the mathematical subject, any subject, but we are talking about the calculus, the multivariable calculus, and basically most of us are going to be engineering students, so I'm not going to define a epsilon delta definition. However, let's try a similar thing with the multivariable function. For example, I want to define for, let's say, my x is two-variable function. Let's say x comma y. So I'm putting x is different from x arrow. X arrow is the vector consisting two values, x, y. And I want to think about what's the limit of these two-variable function, such as that one above. When x goes to a. For example, I can take a as the origin here. How would you like to compute the limit? That's the essence. Actually, Junu said the essence of the limit, definition of limit for the multivariable function. What he said was we need to consider how this x vector approaches to a vector first. And then we have to look at the value at each of these x. So here's a question. What kind of trajectories are there for x to approach a? So for example, let's say we have x is here and a is here. How can you approach x to a? double the x vector, I mean length, double the length from origin to x. And then? How can you approach this x vector to a vector? So a is constant vector. What kind of trajectory? So the question is this one. So what kind of trajectory should we use to approach x to a? What's the easiest way to approach x to a? Uh-huh. Uh-huh. At the same time or in sequel? So he said move the x component of x to the y component of a and y component to a component. But think about you were going to program that. So you have to make it more precise what you mean by move your coordinates of x and y, coordinates of x. What's the easiest way to move this point to this point? What's the easiest trajectory? Uh-huh. And then? Right, shortest way is to connect by straight line, right? Yeah. Right, so you can approach your x vector to a vector by along the straight line. That's the only way to go. So is that all? Is that the only trajectory that we can move x to a? Uh-huh.
Then we could double up x vector.
I mean, if you are in here, you can follow the same line. But I'm telling you, even if it's on the line, do we always have to move my x to a along the straight line on the shortest path? No, I'm saying the possible way. I'm not saying that it's efficient. I'm not considering efficient trajectory. I'm considering all the possible trajectories. Why can't I use like this trajectory? It's possible, right? So think about in single variable function. Why do we care about left and right limit? Right, exactly. So I want to everyone to hear what Jaeyeon and Junho says. So I'm going to leave my second mic here. So what Junho said is, I asked why we need to consider left and right limit, and Junho's answer is, we have to consider all possibilities of possible limit from any direction, right? How about in second two-variable function, our domain is in two-dimensional space. We have to consider all possibility of the limit for every possible trajectory approaching to A, right? So if the limit value of the function are all same for any possible direction or any possible trajectory of x approaching to a, then we can say the limit exists and the value of limit is one of the limit from the trajectory. So the answer, short answer to this question is there are infinitely many trajectories that I can approach my point to A. And I cannot consider every trajectories because it's so many. I mean, it's impossible. The question is, how do I know when there is no limit of the function? For example, let's say this function. So if I want to conclude that there is no limit, how do I know there is no limit? So let's reconsider again the limit of a single variable function. So there are two possibilities of not existing the limit. First one is that you can have a function diverges at the point. So limit is nothing about the existence of value at that point. You don't care about what the value of function is at that point. You care about what happens when you approach it to that point. So one possibility is divergence, and other possibility is when you have, what other possibility you have when you don't have a limit? When
both sides are different.
right, left and right limits are different, then you say there's no limit. So in this case, you can, if you want to argue that there's no limit, you either find a trajectory that makes this function diverges to infinity or negative infinity, or you find two trajectory which converges to two different values, right? So let's try to think about easy one. So we are talking about 0, 0. So my A is the origin, and I'm approaching this origin to any random point. And let's try to approach along this straight line. And my random point is, for example, 1, 1. So I'm going to approach this point by taking the points in between these 2 points as t, t, where t is from 0 to 1. Then when t is 1, I'm at the 1, 0. As t goes to 0, I'm making x at this point, xt, to approach it to 0, right? So I'm going to see what happens to the value of function when I move my xt to 0, 0. So let's say, so x value is t and y value is t. So it means that it is approaching to the origin along the straight line parallel to y equals to x, right? And let's plug in that point. So we have numerator becomes 2t. And how about denominators? Right, 2t squares, right? So square root of 2t. So I'm taking t from 0 to 1, so it's always positive, so I don't have to put the absolute value sign. And the limit is when, so in order to have x goes to 0, I need to take t to 0, right? But t cancels out before I take the limit, so it's going to be the constant limit, which is square root of 2. Now, this is not the only trajectory that we can possibly think of. We can find another trajectory from another point. Let's say I want to take x0 as minus 1, comma 1 over 2. Okay, so and then I'm moving my point from here to here. So let's take this path. It's the same straight line, but it's going to be the different formula for x and y. So when t goes to 0, I want to have that point. So right, well, let's say I'm taking t here. And how about y? I'm going to take y as, let's say minus t, in order to make it simple. So I'm taking t from 1 to 0, then it's starting from minus 1, and becomes 0. And y is just half of t. Let's try to plug in these formula into our formula function. We have the limit of minus t plus 1 over 2t. And in the denominator, we have t squared plus 1 over 4t squared. So the limit is when t goes to 0. That's because that's how we can make this function, the point x comma y, the approach is to 0. So let's take a computation here. So it's negative 1 over 2t. And how about here? We get square root of 5 over 2t. Now, t is positive number. I don't have an absolute value sign. But before we take the limit, let's cancel out t. So what's the result? Minus 1 over square root of 5. Right? Are they same? They are different, which means that the value of function is differed by the trajectory where we approaches to x, approaches to 0, 0. So what's the conclusion? Limit. Right, so that's a good expression. There's no convergence in the 0, 0. And also we simply call it there is no limit at 0, 0. Right? All right, so this is how you disprove the limit, existence of limit. In order to prove there is a limit, you have to use the mathematical definition using the epsilon and delta. And I'm not going to do that because most of the function that we are dealing with will become a function that has a limit and also will be a continuous function. So there's no need to prove some weird function is continuous or has a limit in throughout this calculus course. If you're interested, you can take analysis course, mathematical courses. I think it will be open next semester, I guess. So it's a senior class. So go to that class to learn more about that. But for now, we still have this issue. I want to see better picture of this function, or sometimes not for this one, but if you have a weird function that is not visible in this perspective, I want to change my perspective. I want to rotate this function. So let's do this. This is a mini project that I'm going to show you. You can also have inspiration from what I'm doing this time and have make it more advanced by what I'm doing today. So before we move on, is there any questions about the limit? Yes?
If two more were developing, can have
any ever function that don't have the limits.
So I guess your question is, if you have more than two variable, how do you check the limit? Or how do you disprove there is limit? Is that the question?
어느 함수든 다변수 그 함수에서 만약에 불연속인 지점에서 어느 불연속인데 극한값을 가지는 경우가 있나요?
Sure. So, a good question. He's asking, is there a function which is discontinuous but has a limit? Yes, I can make an easy answer to that. Let's see. So my domain of function is entire plane. And I define my value will be 0 if x and y are not origin, 1 if x and y are 0. So what's the graph of this function? So entire value is 0 except for the origin. So there's a missing point. And at the missing point, we have value 1. So this is our graph. So in this case, we can just argue that the limit exists at 0 because I can intuitively argue that this any trajectory approaching to 0 in the plane will have a limit to 0 because all the values in this trajectory lines are 0. So it has a limit. The limit is 0 at this origin, but the value of function is not the same as the limit. Does it answer the question? Okay, it's a good question. Do you have more questions? No. All right, so let's move on to this project. Now, I want to show you a funny picture. I put it in the week 2. So if you have done some coding project, you probably understand this cartoon. So you can read the sentences here. When you do coding, if it's not simple, then you probably have lots of packages as a byproduct. And sometimes these packages are not well organized, so even you are trouble having understanding what's going on inside. So once you done the programming, you have to refactor it so that other people or you can understand later better. However, sometimes you have to start from the beginning again. Maybe sometimes it's better than just refactoring it. People call it a spaghetti code that if the code it gets really messy, then you have to start it over. So I'm going to start it over today as if I'm doing the first time. So let's take okay, so let's take a new folder. Make a new folder. Oh, what folder did I choose? Okay, so open folder. I'm going to make a new one. Let's see. Okay. Multivariable and graph. All right. So it's a new one. So whenever you start new project, it's better to initialize your module. So go mod init, and I'm going to initialize it to main module. So my name of project is main. And let's write main.go. And basically I will do the similar thing which I did the previous part, which is I'm going to define the MVF, which stands for multivariable function. So I'm going to make a folder named MVF. I'm inside here. I'm going to make MVF.go, which defines my MVF type. So MVF is a sub-package that I'm going to use in my main project. I have to name it with the same name as the subdirectory. And here I'm going to define my MVF or MVF, okay, as a struct. So this is the new one I introduced, but if you have already read the documentation, the beginning, the tour of Go or other pages in the golang.org, you probably have seen this type. So instead of, let's see, I want to compare the previous work with current work. So let's see, I want to open the previous folder. So let's see. Here, multivariable calculus. All right. So in previous MVF, I defined my type as the function type. So this function is predefined type in the Go. But the struct has fields. So I have to define each field as new types. So in MVF, I'm going to define my formula field. And then also I'm going to define my numVar field. And also I'm going to define my domain field. And I'm going to define my end field. Oh, sorry. What is it? Okay, so end field. And also I'm going to define my file name field. So I have been thought about it over for a couple of days, how to make my function struct in organized way. So that's how I came up. So I will explain why I need this. So for example, formula is the formula of the function. So it's the same type as I defined in the previous MVF type. So I need to take an array of input variable and array of output variable. That's the definition of multivariable function. And also, by looking at the formula, you don't know how many input variables or output variables are there. Because you see, in sometimes I could write my two-variable function as formula of x. So this is, if you're just looking at the formula, x, you don't know whether this is single variable or multivariable. You have to specify how many variables are there. So numVar is the array of number of input variable and number of output variable. So I'm going to use as an int array. And also domain is the boxed domain that I'm going to define a function, because every time you define a function, you have to provide the domain of that formula is defined over. Just giving you the formula is not the function. If the domain changes, the function is different. So I'm going to define array of array, because whenever I have a multivariable function, my domain will look like the product of intervals. For example, in two variable function, I have to define domain as the interval of x coordinates and y coordinates, right? So I'm going to take an array of two arrays, arrays which has two elements. Okay, so interval only have two elements, which is the endpoint and starting points and endpoints. So that's why I put 2 in here. So basically, you can consider this as I'm taking an array of 2 floats, where 2 floats means that it's an array containing only 2 elements. So you shouldn't put the parentheses here. This is for your understanding, and this is it. And n is, you can guess that this is the precision of your graph. Sometimes you probably want to make it more precise, so it's going to be a field. It's an integer field. And also file name. So in previous work, we stored it in the test.png. Sometimes you probably want a different name for the file, so this is going to be the option that you can use to graph it. All right. And let's see. So you see that every name is starting from the capital letter. So you can access these fields and access this type outside of MVF package. So I don't need to define the creating function. But what I want to do is, if I have a type, MVF type, I want to make it able to graph. So, okay. So this is my function. So now here's the question. What we have done in previous work is just graph with fixed x, y, z coordinates in this two-dimensional canvas. I want to make it rotate. So whenever you rotate, you have to provide how many angles, how much you rotate it in certain direction. So think about how you draw this three-dimensional object in two-dimensional canvas. How you can imagine that the two-dimensional picture looks like three-dimensional. So here, let's say we have a canvas here, and here's some three-dimensional object here, and you are looking at through this canvas as if it's a glass, so you can see through this glass on your object. So one way you can plot this three-dimensional object into two-dimensional is by taking all the points, which is obtained by connecting your position of your eye, or starting of the light, where the light starts, and then connecting to the point on this object, and then there is an intersection of this line and this figure, this two-dimensional canvas, and you can connect these dots so that it looks like three-dimensional in this two-dimensional plane. That's the one way to go. And suppose that you have a similar situation. And if you're looking, if your eyes are very close to this 3D object, then this might be giving you the correct figure of this three-dimensional. But however, if you're looking at this three-dimensional figure far, far away, right, then all the line connecting your eye to any point in this three-dimensional will almost be parallel, right? So instead of taking these intersections, I can only just take the projection of the points right onto this two-dimensional canvas. Just simple projection orthogonal in orthogonal way. So you have this kind of figure here. So today I'm going to use this method. Okay, you can consider how to draw. I mean, you can also draw this method, but I'm going to draw this method. Okay. So what's the scheme? So think about three-dimensional space, x, y, z. And let's see, I have some, this kind of plot inside of x, y, z space. And I'm looking at this object through a glass, 2D glass, and doing this projection. Okay? I'm trying to project this three-dimensional into this 2D glass. So that it will look like something like similar thing in here, right? But what I'm trying to do is rotate my glass so that I can look in a different perspective. So how should I do that? So first of all, think about your canvas has absolute x and y coordinate. Okay? You should have your own xy coordinate inside the canvas which doesn't move or doesn't change, so that you can draw that in actual plane. Because even if you move your this glass, if you had your xy coordinate axis, it shouldn't change, because it's the figure that changes, so that so that you feel like you're looking at the different direction of this graph. If your axis change, then there's no meaning of changing the perspective. So the red line, which represent horizontal one, represent the x-axis, and vertical one represent y-axis, shouldn't change. Okay, it has to be the same, which means that if I suppose that I'm changing this glass, moved my glass about z-axis, suppose that I have this configuration, then it has to be same according with the position of this glass. That has to change accordingly. Okay? Does it make sense?
I don't get why those x-axis and y-axis should be fixed.
But because that's the canvas xy axis, xy coordinate for the canvas.
Then it should be y and z-axis, not x and y.
X, y, I mean, this one is the axis for the three-dimensional thing. This one, x, y, is the coordinate for the canvas, two-dimensional canvas. Okay, it's a good point. So I'm going to match this y-z axis with x-y axis in the canvas. But for now, let's think about my glass has, I put a marker and wrote my x-axis and y-axis on the glass, and then try to look at my 3D object through the glass with this xy coordinates marked. Okay, this mark should not change, right? That's how I can draw my 3D object onto this glass, right? Okay, and then let's see, how do I define the orientation of this glass? So I started off from the glass which is perpendicular to x-axis in three-dimensional space. So this is the normal vector, which is orthogonal to the glassy canvas 2D plane here. And I put my orthogonal vector to perpendicular to x-axis at the beginning. I'm going to rotate so that the n changes when I rotate is done. So n will change. This n vector will change. Okay. So I can define my perspective by just setting up what the n is. If I say that n is, for example, 0, 1, 0, then I'm looking at the y direction, right? So in that direction, if there's no 3D graph here, but only the x-axis and x, y, z axis, then what you see through this glassy canvas is just x, y, z axis. You don't see the y axis because it's perpendicular, right? What if you have 1, 1, 1? Well, actually, it has to be normal vector, so I have to divide by norm of this 1, 1, 1. What kind of how would you see x, y, z axis in three-dimensional space when your perspective is orthogonal to 1, 1, 1? Your glassy canvas is orthogonal to 1, 1, 1. So it's like you're looking at here, right? And right in the middle of x, y, z axis. Right. So you can guess. We will actually see how does it look like. You can guess that it will look like here. So this is how you observe from the glassy canvas when you're looking at the x, y, z axis in 3 dimensions. Right. So how about the x, y coordinates drawn on this glassy canvas here? So the canvas is somewhere here. This is x-axis, and this is y-axis you draw. So here, this is x-axis, and this is y-axis. I'm not going to draw this axis. This is an imaginary axis that I'm trying to use when I actually plot this whatever in 3 dimensions. All right. There are lots of things to do before we move on, because if we just fix everything in this position, nothing happens. I mean, everything is simple because I can just project everything down onto the plane, which is parallel to y-z axis, which means that I kill every x coordinates in this of the points on this graph. So nothing. It's very simple, but you don't see the proper figure. What I have to do is to think about how to rotate this canvas. I'm not rotating the graph. Graph is here. I'm just rotating my canvas. So for example, I want to rotate my glass, which was originally perpendicular to x-axis, to the position where it's perpendicular to 1, 1, 1. How would you do that? So I'm going to give you a hint by telling you, by introducing a new coordinate system. We have x, y, z coordinate system called Cartesian coordinate system. There are two more, which is cylindrical coordinate system cylindrical coordinates, and one other is spherical coordinate system. So cylindrical coordinate system measures the XYZ coordinates using r, theta, and z. So as if your point is lying on the surface of cylinder, if you project that down onto XY plane, this point can be identified with the radius of your cylinder and the angle from the x-axis. So radius r and theta defines this projection. And the actual point has z coordinate, which is same as z coordinates. So x, y, z can be identified by r cosine theta, r sine theta, and z. So this is coordinate system called the cylindrical coordinate system. And the spherical coordinate system probably learned from the physics, but let me explain it again. So we have x, y, z axis. And suppose your point is on the surface of sphere of radius r. What's the x, y, z coordinates? So project that on xy plane. Then there are three things to measure. First of all, the radius, which is the distance from the origin to the point, is defined here, r. And you can measure the angle between z-axis and the line connecting between origin and the point. So that will be the theta. And you have a point obtained by projecting your point onto xy plane. And the line from origin to that projection point makes an angle between x-axis. So that will be called phi. So that's all we need. First of all, we have the length of this line as r times what? So if you're making a right triangle right here, this length is equals to this length. And how would you compute this length? So this here is a right angle. Right? R times cosine or sine? Sine. And this is the radius projected on xy plane. And we have an angle phi inside of xy plane. So x, y, z will, first x will be the radius r times sine theta times cosine phi. Okay. So this is angle of the point, this is the radius of the projected point on xy plane. So it should be the same for the y-axis, r sine theta. But for the y coordinates, we should put sine phi. Right? How about z-axis? How about here? Cosine theta, right. Okay. So we have new coordinates. Let's go back to how we can rotate our canvas from normal to x-axis to 111 direction. Mm-hmm. So when you rotate, you don't want to dilate or squeeze these axes drawn on the canvas. And also you don't want to change the length of the axis here. Okay? So you have to make a transformation continuously in some directions. But easy way is somehow you can find out way to transform your x-axis to this vector, 111 vector, or divide by square root of 3 in the shortest way, right? Somehow you can imagine that you can move your 100 vector to 1 over square root of 3, 1 over square root of 3, 1 over square root of 3 vector in some shortest path trajectory, right, along the sphere. It's kind of ad hoc, right? It only works for 111 vector, right? I want to make it general. I want to make a scheme that works for general situation. So let's try to find out how to move my 100 vector to this vector using two types of rotation. One is rotating about z-axis, like you're turning your cylinder here, and the other is rotating about y-axis. Supposing that you have two kinds of cylinder. One is parallel to z-axis, and the other is parallel to y-axis. So rotating about z-axis means that you're moving along xy plane, and rotating about y-axis is moving about xz plane, like this. Okay. How do you combine these two rotation to move 100 to 111?
We could do it by two steps.
Uh-huh.
First, we should rotate by the z-axis,
Uh-huh.
then rotate vector a.
Rotate back to the n by rotating about which axis? Actually, that was my first thought before when I prepared this idea, and I was stuck at the second rotation because I cannot make any of these two rotation, or three, even three. So which means that if I start from here and then rotate about z-axis, I'm making 45-degree vector, and I try to make it upward to close to z-axis here. So this is first and second step, and third step is to somehow lift this vector in some angle so that it will point 111. But then this part, moving this second step vector to third step vector, cannot be done by any of these rotation. Even if I introduce one more rotation, which is the rotation about x-axis, I cannot do that. It's actually rotating about new axis, which is perpendicular to z and this vector. So I have to make it a very complicated rotation. So, however, let's think a different way. How about we use rotation about y first? So you're starting from 1, 0, 0. You lift it, and then you rotate. So it will be rotation will be rotating your vector along this cone. So somewhere in the cone here will be 1, 1, 1. If you lift the first vector, the second vector with enough angle will be pointing 1, 1, 1. The angle that you have to rotate your second vector to the third vector is 45 degrees. But you have to compute the angle from 1 to 2. What will be the angle? What's the angle here? So the rotation from 2 to 3 is 45 degrees, so pi over 4. How much should I rotate from 1 to 2? 45 is not the correct one. This one is divided by 1/3, right? Well, let's think about it later. We have a scheme. This is hard, so let's use this one. So I'm going to apply rotation about z and rotation about y. Okay. So how do we transform a vector by rotation? So let me erase this. We have to think about the cylindrical coordinate again. So for example, I'm taking a rotation about z-axis, and here we have, let's say, r cosine theta, r sine theta, comma r is somewhere here, right? And so this is r cosine theta, r sine theta, and z. After rotation, let's say I'm rotating by phi degree, then it will move to the point where r cosine theta plus phi, r sine theta plus phi, and z, right? So let's rewrite this point using trigonometric equations. So when you have an angle sum inside of cosine, this is cosine theta, cosine phi minus r cosine theta, sine theta, sine phi. And this one is r cosine theta sine phi plus r sine theta cosine phi and z. Right? So we don't do anything on z, but we have changing my original vector using some linear combination with coefficient cosine and sine phi here and here. So these parts are coming from original coordinates, right? This one comes from here, and this one comes from here. So there are easy way to express this kind of linear combination using matrix multiplication. So I have to introduce some matrix here. So you see, I don't even have to teach what's the vector, what's the matrix. If you're just starting from what you want to do, these concepts generally or naturally comes out. So it's better to learn this way than starting from the definition. We have a goal. We want to grab something. It just happened to have we should learn the matrix multiplication. So I will just give you the example. I don't have to give a definition at first. So for example, let's say I want to multiply two matrices. Basically, the matrix is the collection of values in the R rows and some rows and columns. So let's say we have 0, 1, 1, minus 1. So this is 2 by 2 matrix, which means that there are 2 columns and 2 rows. Let's say, okay, so this is just mentioning that the first 2 is the row, and second 2 is the number of column here. Okay? And every matrix looks like this. So if you have an n by m matrix, n is representing the number of rows, m represents the number of columns, and there are nm number of elements in this array. Now I can make a multiplication with a matrix if the order of multiplication satisfies the following. So we have 2 columns, right? Then the matrix that you're going to apply the multiplication on the right should have the same number of rows as the number of column in front. So you should have, let's say, 2 by 1 matrix. Then you can carry out your multiplication because you have 2 columns in the matrix in front and 2 rows in the matrix in the second. So you can carry out the multiplication. The way you compute this is try to choose row in the first matrix and column in the second matrix. So you choose the first row and first column in each matrix. And then since there are same number of elements in row and column, you're multiplying each element and add them all. So here we have first row, first column. So whatever the result goes to in first row, first column here. So I'm taking 0, 1, and multiply each other. And then 1, 0 here, and 1, 0 here. Okay? So this result, which is 0, goes to the first row, first column place of our new matrix. And you take the second row and first column here. So there's no other column than the first one, so you only get the first column in the second matrix. So what goes here is 1 times 1. Okay? You take a multiplication in sequel in the same order as row and column has, and minus 1 times 0. So basically it's 1. So happens to be 0, 1. So what's the result? Whenever you multiply 2 matrices, the middle disappears, and the size of new matrix is the same size as row of the first matrix and column of the second matrix. So it's a 2 by 1 matrix. Is it clear? It's very simple. So it's not hard. Let me just give you the general definition. Suppose that I have a matrix A1A whose element has A1, M and A M N1 and up to A and M. So when I write this way, I'm saying that this A11 is an element of first row, first column of the matrix A, and so on. So when I change my column, my second index is increasing from 1 to M because there are M columns here, and there are N rows. So when I move the rows, I'm changing my first index increasing. Okay? And then I want to multiply another matrix called B. So B has M rows in order because I want to make it a multiplication. So B11 to BM1 and B1L and BML. So A is N by M matrix and B is M by L matrix. Okay. So even before you carry out the multiplication, you can guess that the result will be N by L matrix. So what's the result? So in between here somewhere, you will have an element at ith row and j's column. Right? This Cij is obtained by taking ith row in the first matrix and j's column in the second matrix, and then multiply one side by side and then add them all. So what's the Cij? So Cij is take ith column, so your first index of A will be I, and then take the first element, which is in the first column, and then you take the first element in the jth column, which is on the first row. So you take B1j, okay? Then do the same for the second element, which is AI2 and B2j, until you get mth element, which is AIM and BMJ. So this is your Cij for I from 1 to M and N and J from 1 to L. Okay? In the summation notation, you can write this as K from 1 to M, where you're taking AIK and BKJ and multiply and sum these all. So this is definition of matrix multiplication. Why we need this? So go back to our purpose here. We have a new coordinate which given by linear combination of old coordinates. I want to make it as a matrix multiplication. So let's take our old coordinates as a coordinate of 3 by 1 vector, a 3 by 1 matrix, r cosine theta, r sine theta, and z. And I want to make a multiplication on the left by 3 by 3 matrix. So I get 3 by 1 matrix, and the result should be our new coordinates. R cosine theta cosine phi minus r sine theta sine phi. And here we have r cosine theta sine phi and plus r sine theta and cosine phi. And z is same. So let's guess what should be inside of this 3 by 3 matrix. First of all, in order to get the first row element, I should take first row in the first matrix and then the first column in the second matrix. So r cosine is here. What should be in the first column of the first matrix? Cosine phi. Let me write this way. And how about the second? Minus sine phi. And how about third? 0. We don't have z here, so 0. How about the second column, second row? Sine phi cosine phi 0. How about the third row? 0, 0, 1. Great. This is our rotation matrix. This will be very useful when you do physics or in mechanics or robotics. It's a basic. So it's a rotation about z-axis. What if you rotate about y-axis? Phi. What if you want to rotate about y-axis? Without doing all this again, can you guess what the matrix looks like? Right. So y row represented by first row, right? So you're switching the row of z and y, right? So you're switching the elements row, second and third row and second and third column. That's the same effect of changing the role of y and z, right? So let's see. Do the same. Minus so this is the rotation about y-axis by phi. Okay. So go back to our small goal. Our big goal is to graph this thing. The small goal is to move my 1, 0, 0 to this vector using the rotation. So we define 2 rotations, and we had a scheme to how to apply the rotation. First, you apply the rotation about y-axis, and then rotation about z-axis. So in order to carry out that computation, you can do by your hand, but we want to do it on the program. So let's define our package. So I define MVF as a function package. I want to define a vector package in order to define all this multiplication, matrix multiplication, and so on. Okay, so new file. I'm going to use a matrix go. So the file name doesn't have to be the same as package's name. The reason why I used the vector as a package name is I'm going to use other the properties of vectors, which is the projections and so on. So for now, I'm just giving you a definition of matrix package, matrix type. So package vector. Inside of matrix go, we have type matrix. So it should be also, let's take a capital here, so make it public. So I'm set that the matrix is nothing but a collection of pair of n points and n column and m rows. So it should be represented by arrays of arrays of float values. What should I do is defining the matrix multiplication. So the reason why I make the type this arrays of arrays as a new name matrix is because I want to make a method that applies to any matrix type. So whenever I take a matrix M, a small m is the name of matrix that I calling this method, I'm taking a multiplication of with another matrix. It's auto completion here. And then, so result is another matrix. I have to spit out another matrix. Okay, so for now, let's make a new function, which makes empty matrix or zero matrix, all which is containing taking n and m as integer value, which represent the number of row and number of columns, or maybe I should say this is r, this is column, so that we don't confuse. And let's see, I want to make a new matrix zero with zero entries. I have to define my arrays here with r column and r rows and r columns. So I'm going to use the outmost array as a row array and inner array as a column array. So let's say I'm going to make a float 64 r number of float value here, and for each of r I'm going to define another float c number of floats. Okay. In that way, what I'm doing here is I'm making an array with r memory allocations defined. So I'm pre-allocate my memory to be used as an array of float named by rm. And then inside of that array, each element is another array, which pre-allocates this c number of memory blocks. And then I'm assigning that at the ith array of m. Okay. So by doing this, I cannot use more than I pre-allocated. Okay. But by doing this, I can secure my memory blocks to use as my variable. So it's a good way to do this if you definitely know how many memory block you're going to use. And then, okay, so after multiplication, I will get a matrix of size m and number of rows of m and number of columns of n. So you see, when I take the len of m, it gives you the number of elements inside of that array. So when I define my matrix, the outer array is the number of row, representing the row, and each row consists of array which represent the columns. So number of the number of row is simply the length of this array m, and the length of n is number of rows of n. I want the new matrix to have the number of columns same as number of rows same as number of rows of m, and number of columns same as number of columns of n. So I have to call the number of columns of the second one. So this is the number of rows of m. This is number of columns of n. Okay.
What is the zero between those?
It's a bracket. All right, so and then let's take this definition, the matrix multiplication definition. For every I is the index for the row, and j is the index for the column. 0. And then L is a new matrix that we're going to store that as the matrix multiplication. matrix, and we're going to define the value of Lij, which means that i's row and j's column entry. But for that, we should perform this summation. We cannot put the sum in this formula because we don't know how many terms that we're going to use right now, because it depends on the value that we are taking in inside of this method. So I'm going to define not integer, sorry, float value called sum as what I'm going to use for the sum. So it's 0. It is set for 0 at beginning. But I'm going to use this summation notation, this one, from 0 to, so how many sum ends do I have? Same as the number of columns of, in this case. So I'm taking m times n. So m is the first element matrix. So number of sum ends is number of columns of the first matrix, which is length of array of m0, right? You have to think through it once we have finished why I'm doing this carefully. And then each sum end we have to take is the following sum. So aik, bkj, right? Here I used n and m, so it's nik times mkj. Okay, so I'm taking so plus equal sign means that I'm adding more to this sum variable. Okay, and then once I'm done this, I'm substitute this sum to the ij element of L. So that's it. So once we've done this, I have a new matrix with different values here. I have to return this L. Okay? So that's a matrix multiplication. And let's try to check whether we have done is correct or not. So what we have done, what we have set is first define this vector and then try to multiply these two rotation matrix and see if we get the desired result. So first of all, let's say I want to define my V to be new matrix of 3, 1, 3 times 1 size matrix, because I have to make a multiplication in the column form. Okay, so 3 times 1. I didn't import this package as my the sub package, so that's why I have a red warning here. So now leave it here, and also I want to change the value here. So we have two components, a row and column, but column has only have 0 entries here, a 0 index here. First is 1, and second is 0, and third 0 is already defined, so I don't have to put the 0 again, because whenever I call a new matrix method, and it automatically, if I make the float value initialized, then it initialized as 0, so I don't have to put the 0 again. So this is how you define 0, 0, 0 vector as 3 by 1 matrix. And let's define two rotation matrix. Let's see. Let's say T1 going to be pi over 4, and let's define, how do we call it, M1 as vector new matrix 3 by 3. So this will be the first matrix, first rotation that we're going to apply. So this is going to be the form of M1. So except for 0, I have to assign values in these places here because everything is 0 now. So M1, 0, 0 is math dot cosine T1. So I'm using T1 as phi in there. So, okay, T1 is new variable, so I have to put it this way. And also M1, 0, and so the second one, S minus S phi is 0, 1, 2, so it's the second index. So it's a math minus math dot sine T1, M1, 1, 1 is 1, M1, and 2, 0 is math sine T1, and M1, 2, 2 is math dot cosine T1. All right, so I didn't import math, so there's warning and no warning. All right, so M2, do the same thing here. Vector new matrix 3 by 3, and M2 is now of this form. So 0, 0 is math dot cosine. So I should use another angle. So let's define T2 as another angle. I'm using same pi over 4 because that was our guess in previous, before we actually start programming. That's how we guessed to obtain 111 over square root of 3 from 100. So let's see how it goes. All right, so M2, 0, 1 is math minus sine T2, and M2 of 1, 0 is math sine T2, M2 of 1, 1 math jump cosine T2, right? All right, that's all. Now we have to make a multiplication. So M2, so let me write that here first. So we have V as our vector starting from 1, 0, 0, and apply M1 and then apply M2. In principle, you have to do in this way, but it's a theory or just a proposition from the matrix multiplication that you can do this way, M2, M1, and then V, okay? So it's an association rule that applies to the multiplication of matrix, that you can carry out your multiplication in any order as long as you keep this multiplication order. Okay? All right, so I'm going to do that way. So M2 dot multiplication of M1. So when I'm done this, I'm getting another matrix. So it has a method which can apply the multiplication and V. All right, this is our final result, and let's see what it is by printing out this array. So FMT is not defined. FMT here. All right, so no problem here, and go run main.go. What's wrong here? So index out of range 1 with length 1. So matrix multiplication is having trouble. Let's see, 3 by 3, 3 by 1. Did we have any problem? No. M, N. J, K, M1. Oh, I forgot the M. This is M and this is N, sorry. So I'm taking M times N, so right, this is the right way to do this. Okay. All right, let's do it again. Go run main.go. All right, what we got here is 1 over 2, 1 over 2, 0. Not what we want, right? So if you had this 111 over 3 square root of 3, it should have the same value, like 0.7 something for 3 components. So again, our scheme was to rotate 1, 0, 0 along y-axis to get this one, and then rotate along this cone to get 1, 1, 1. So I guess the second rotation, the angle of second rotation should be pi over 4. Intuitively, it should be true. How about this angle? So we set this as a pi over 4 in our program. Does it really a pi over 4? It needs a calculation. Anyone from online? Anyone from online can answer what should be the angle? (60 degree? Well, you can check 60 degree again. So that's the T1, right? That's T1. So pi over 3. Not still. Not. Oh, it's weird. So pi over 3. Why is it give? Why does it? Is it norm 1? Norm 1 vector? T1. Oh, I forgot 1 here, so I forgot to put something here. So it's T2, 2 has to be 1. Okay. All right. Well, let's try pi over 4 again. What happens first? Okay. Yeah, okay, so at first, 1 over 2, 1 over 2, 0 is not norm 1 vector. We should have a norm 1 vector. Norm should not change, but now it's changed. So this is correct answer, this one. But still, it's not 1, 1, 1. It's different. How about we try pi over 3 as Juno is suggested. Let's see what happens. Not quite similar, 1 to 1, 1, 1 here. Can anyone guess? Can you guess? I think it's a good problem for high school kids. Kind of. I'm not saying this is easy questions, but something that you can think hard, but not require many knowledge. Just need to think correctly. Right. So let's think about the angle here. So here, this angle is as same as this angle, right? So when you project your vector on xy plane, so you're changing the set of these two vectors to these two vectors. Angle should not be changed by rotating about z-axis. So try to think about the triangle here. So this is right triangle, a right angle here. Try to think about all the length of this triangle. What's the length of this side? 3 square. We're taking the norm 1 vector here. 1, okay. How about this one? 1 over square square, 1 over square square. And the last one? 0. So what's the length here? Yes. 2, say it again. Let me make a bigger picture because I don't need this anymore. We're not going to be able to do this today. So let's make a bigger picture. So x, y, and z, and this is my 111 over square root of 3, and this is so length 1 and length. Can you say it louder? 2 over 3 root. Yes. How about this? Actually, we don't need this, but anyway. 1 over 3 squared, right? We want this angle. What's this? Arc cosine. You have to use arc cosine. Let's see. That's T1. So math.a cosine. So math package has this arc cosine already defined. So you have to put a value of cosine to get the theta. What's the value of cosine? Cosine value cannot be larger than 1. I mean, you have to put a cosine value to arc cosine to get the theta. Which square root of 2 over 3. Square root of. Now, be careful when you put 2 over 3 like this. So this means that you carry out integer division. So 2 over 3 gives the integer result. So it's going to be 0. So it's not going to be the right answer. So you have to put math square root of 3 like this. All right. So let's go run main.go. Now we have same 0.57 for x, y, z coordinates. That's 111 divided by square root of 3. Okay. Now we have proper transformation works. What we have to do is translate right, so all we have to do is translate the coordinates that we drawn onto the glassy canvas according to these rotations. And then project the points on the 3D space to the rotated canvas. We're going to do that next time. Okay. All right, so thank you for listening, and if you have any question, please ask after the class. All right. See you next week.